Hello, friend. Welcome. In this video, we're going to start on an important topic. So we're going to be talking about what are known as transformers and the transformer architecture. And we're also going to be talking about a mechanism called neural attention. Okay. So if you're interested in, after this class, getting deeper into understanding what generative AI and large language models are all about, these topics are important because these form the building blocks of generative AI systems. So in particular, word embeddings that we already talked about, and embedding spaces, the transformer architecture, and neural attention are all kind of important concepts that are used in generative models and large language models. Okay, so let's go ahead and begin and start talking about our topic. Okay, so first, just a real quick little bit of history. So started in 2017, a new model architecture kind of appeared, and it really made a big splash. So it first made a big splash in text processing. Okay, so as we'll talk about, the transformer architecture is, at its heart, it's really a bag of words model, although you can extend it to add in position information. So it's a bit of a hybrid. Like we hinted at before. All right. So the paper, I encourage you. There's a link to this in the bibliography for the slides. The attention is all you need. Was introduced this idea of neural attention. Okay, so this was an important paper in this area here. The neural attention mechanism we'll talk a little bit about here, try to give you an intuitive idea of what it's about. So with this, you could build powerful sequence models. So it made its first big impacts in text processing and language models that didn't feature any recurrent layers. Okay, so it's not really using the concept of recurrence. It's using this attention mechanism to get all of its power. Okay, so this idea of attention has fast become one of the most influential ideas in deep learning. Models should pay more attention to some features and less attention to others. Okay, so that's the basic idea. So let's see how this works here. So you are familiar with the idea of attention, how we generally mean it. Okay, so just as a quick example, as you're reading, you're gonna have an attention mechanism. You're going to skim some things because you already know them, or depending on what your goals are for reading some text and getting some information. So depending on your goals, your interests, and your background, that will your focus of attention will be different, right, from other people, or different from when you first read a document to maybe come back later on. You might have different goals and things, right? So attention is important for you looking at a document and understanding it. Okay, so what if a deep model could do the same, or any kind of model that you want to have artificial intelligence? So not all input information seen by a model is equally important to the task at hand, and we can build in a kind of attention using this neural attention mechanism that was introduced in the paper I mentioned. You can make an argument that some of the mechanisms we looked at previously are kinds of attention mechanisms. So the pooling layers in convolutional networks, I describe them as doing some downscaling. But you can think of, for example, max pooling. If you're max pooling over a 2x2 over 4 features, they are a type of all or nothing selective attention. So for that particular window, the one with the maximum is the one you pay attention to. The TF-IDF normalization that I looked at, I probably should have emphasized a little bit more, but it's a kind of assigning an importance score to each word in your sequence, right? And that token score is based on the word in your current document, but also how frequent that word is in your corpus, right? So even if you use a word a lot, like the or a, if it's very frequently used in the corpus, it's not going to get a high normalization by this mechanism, right? So it won't be considered important. But if you use a word a lot and it's a word that's not real common in your corpus, it will get tagged by this sort of normalization as something that you should pay attention, or the model should pay attention to. Okay. So attention can be used for more than just highlighting or erasing certain features. Okay, so the purpose of this slide is to give you an intuition of what neural attention is doing, and then we'll go into a little bit more of the details of how it actually works in deep networks. Okay, so the idea is that the question was, can we make features context aware? So back to the idea of a word embedding space. So in an embedding space, it's not correct the way we looked at it before that a single word has a fixed position, a fixed relationship with every other word. I mean, that's the embedding space that we looked at previously. That's true. That's how words are represented. They're always going to have a fixed relationship with every other word. But in reality, that's not true. Okay, the meaning of a word is context specific. So really, it should its position in the embedding space should shift depending on context, depending on what we're doing right now, and depending on the other words around it. So in a smart embedding space, it would provide a slightly different representation, vector representation, for a word depending on the words that are found, the other words are found around it. Okay, so that's what the self-attention mechanism for deep networks actually does. So the self-attention modulates the representation of a token in a word embedding space by using the representation of the related tokens around it. Okay. So you can do a similar thing for visual kind of data. So in a visual space, it might look something like on the left-hand side. So attention might focus in on particular areas of the image. You might make an argument that that's a little bit what the feature filters and convolutions do, right? So, based on attention scores, we have to have some mechanism to calculate attention scores. And in a visual space, that might mean that you focus in on particular areas, like on facial features in this case, versus other areas of an image. So the way that this self-attention mechanism works in practice is you can think of it as having three basic steps. Okay, so think of, we're processing a sample, and think of this, that we're doing some sort of sequence processing. So we have a sample like the train left the station on time. So these words, we're using a word embedding space like we've discussed before. So these get translated into a token. Each one of these single words is a token in, like, let's say, 100-dimensional word embedding space. So that's that's what these things up here represent, is the token embeddings in a word embedding space. Okay. So so we're just focusing on the word station here, okay? So we would do this for every word in the sentence, but so the first step is we need to compute a relevancy score, all right? So a relevancy score between the vector for station and every other vector in the sentence, all right? So we'll go into a little bit more details of how you compute that relevancy score in a bit, but basically, it's just the dot product of our word vector for station and all the other vectors, okay? So that is like the result for the column for station here. This is just the result of doing the dot product between station and we got a 0.2. And the dot product of between station and train maybe gets a relevancy score of 0.8 and so on, okay? So, again, just a little bit, if you know how dot products work, that makes sense. And this is a common method that was used to give an attention score or a distance score between two words in an embedding space like this. So if your embedding space is created in a good and meaningful way, the dot product between two words that have similar meaning should be high. And the dot product between two words that are orthogonal, that have no common meaning between them will be 0 or low. So that's what we're showing here, and that's what we're relying that our embedding space will do if we use the dot product to compute this relevancy. All right. So the result of that is really the relevancy. So this square matrix over here is the result of doing this for all the words. So we would compute the relevancies for the first word against every other word in our sample, like a sentence, and then for the second word and so on. All right. So let's focus back in on the word for the station, how we're going to modify its representation. Okay, so after we compute the relevancy scores, we would actually apply some scaling and do a softmax. So for example, this is necessary because we're going to our second step is to add to sum up all these vectors in order to get a new representation for station. All right, so this is really kind of a weighted sum of the vectors. So for example, like the softmax and the scaling would result in a probability distribution. So the sum of these, just looking at the sum of all of the vectors, their relevancy to station would sum up to 1. Right? But then we just sum up these vectors, and that's going to be our new vector. It's going to be the actual vector that we use to pass on to our learning layers for station. Okay, so this is no longer going to be the same as the original embedding for station here. So it's slightly modified. Because, for example, just when we add together, say, station and our representation for train, our new representation is going to be in the context, so it's going to be moved towards. It's going to be a little bit more similar to train in this context. So that will help a learning model know that in this context, station is the kind of train station instead of some other meaning of station that we might run across or might have in a sentence here. So that's found out to be very valuable for passing on to the type of recurrent layers or other layers that we talked about. So in summary, that calculating the relevance scores or the attention scores and then doing a weighted sum of them, the result is a new representation for every word, including station. So a representation that's slightly different from the original one that incorporates the surrounding context. So they're going to be, each one is going to influence all the other ones, and they'll pull themselves together in our original word embedding space. And this can very much help understand the context for layers that use this later on to perform learning. Okay, so, and if you're like me, looking at this in kind of pseudocode or code can really help you understand. So to try and get even a little bit more of a detailed understanding, let's look at the kind of the pseudocode, how this might be implemented in Python, for example. So for the self-attention mechanism, imagine that we're inputting a single sequence, so just a single sample. Right. So again, these are coming in those word embedding space. All right. So what we would have for when we're doing sequence processing like this is we would have something that looks like some number of whatever the maximum tokens are that we were using for our sequence length. For example, in previous examples, we cut it off at 600. Right, so the first 600 tokens. If we had less than 600 tokens, we would pad it. For every single token in the sequence, if we're using a word embedding, we would have, for example, 100 dimensions, which encodes that. This for row 0, that encodes whatever word 0 was in 100-dimensional space coming in as input. So the output from this self-attention mechanism is going to be the same size as the input. So we're going to be returning 100-dimensional vectors again for every one of our input words in the sequence. So word 0, 1, 2, 3. but the return dimension is going to be slightly altered by this self-attention mechanism. All right. So in pseudocode, this would look something like this. So we're going to iterate over every word in the input sequence. So here, pivot vector for the first time in this iteration would be the embedding vector for word 0, so the word at index 0 in our sequence. Right? So we first do that. Step 1 I talked about, we calculate the relevancy score or the attention score. We're going to do that for every vector in the sample as well. So we have an inner loop here that does the same loop over all of the input sequence. And then attention is really just the dot product between the vector that we're currently trying to get some more context for and every other vector in the input, right? So we end up with 600 scores, the dot product between this pivot vector and every other one, right? And then we're going to square and do a softmax. So we actually, so there's kind of some normalization. This is important, and then we do a softmax. So the resulting thing is actually a probability distribution over all of our 600 attention scores that we have here. So if we didn't do this, when we sum these up, we would end up with vectors that were of wildly different sizes than kind of in our original embedding space. So we have to do some sort of normalization like this. Right? So step 2, then we're just summing them up, right? It's a weighted sum. So we take multiply the score times each of the input vector and sum those up. So, and if you remember back to our previous slide that we were using, so for example, the one that's going to have the highest weighting, so when you do a dot product of a vector times itself, it'll be 1. But other vectors that are similar will have high scores, and ones that aren't really related to them will have low scores. Okay? So, but yeah, so the result of that sum will be, it'll be a weighted sum. So we'll take the vector times its score. It'll be 1 times the one that's times itself. But these weightings will be low for things that don't really give us any context. Right? And that's the output, right? So then the output for vector I is the result of this weighted sum, times our leveraging our attention score. So Keras basically has a built-in layer that implements this self-attention mechanism that we just described here. So, I assume, of course, it implements it in a way that has good performance, so it's probably not iterated like this, so vectorized implementation, but of the basic concept that we talked about here, right? So that layer is called MultiheadAttention. Right? So it actually takes kind of 2 parameters you have to specify. So number of heads, we'll describe that in a moment here. Of course, you need the embedding dimension. So, if we're using a word embedding space of 100 dimensions, you would need to pass that in. So what this does, though, is it takes inputs, like we described here, and they're going to come out as output in the same shape. So our inputs might be, batch size of 32, where there's sequences of 600. So this only refers to the last dimension that comes in, the embedding space size. And they will come out in exactly the same shape they came in, but the resulting vectors will have been modified by context, by this attention mechanism. All right. So if you look at this closely, you might ask, what are the multi heads here? So why did we specify 4 heads? What's that mean? The other thing is, you might notice that unlike other layers, the output the input is passed in 3 times. What's that all about? So why are we passing that in 3 times? Okay, so a little bit more about attention. Some details about that multi-head layer and what it means. So we're going to get to the transfer architecture in the next video. I'm going to split this into 2 here. So the transformer was originally developed for machine translation. So it was a sequence-to-sequence model. So it was designed to convert one sentence, like say in English, into another sentence. say in Spanish. So that's what the example we'll use that we will turn to when we look at the transformer architecture. Okay, so so the self-attention mechanism that we described can be generalized in this manner. So it really performs schematically that it's taking the pairwise scores. So we'll call that. So for each token in inputs A here, it computes how much that token is related to every token in input B. Okay, so that was really in our pseudocode before. That was the dot product between the pivot vector and every other vector in the sentence. So we were using the same inputs for both the pivot and the how much it was related to other things in the same input. And then we computed a weighted score of those. So we used those scores to make a weighted sum of the tokens from input C here. Okay, but again, that was just itself. So we were doing that to reweight the input themselves in our previous pseudocode. But in the general case, all three of those can be different. Okay, so in the general case, there's nothing that requires input A, B, and C to be the same input. So we call those the query key values. So our general case is that we're going to have some query that we want to get this relationship, that mechanism between the query and the input keys, and we're going to sum those up to get a new set of values. Okay. So in summary on that, conceptually, that's what the transformer style attention is doing. You've got a reference sequence that describes something you're looking for, that's the query, and you've got a body of knowledge that you're trying to extract information from, that's the values. So each value is assigned a key that describes the value in a format that can readily be compared to the query, and then you simply match the query to the keys and return a weighted sum of those values. So that's the most general case. Okay, so finally, a few more details. So you don't have to be too concerned if you don't get everything that's happening here on this multi-head attention layer. But this is just so you kind of get an idea of why it takes 3 inputs. So that's so it has that most general case can work in when we have a query key value coming in. Okay? So there's some other things to know about this multi-head layer. It's not actually stateless like I sort of implied previously. So there are some trainable parameters that will get modified in here. So each of the heads, so that was the first parameter that we talked about. Each of the heads in one of these multi-head attention layers has an independent set of weights. So there's a little bit of similarity to this and the depth-wise separable convolutions that we introduced last time. So you can't have just one head, but you can have 2 or 3. You can think of these a little bit like the number of units in a hidden layer, or the number of output filters that you want, like a convolution layer, to learn. All right? And that's the number of heads. But each one of these is doing a similar thing to what we talked about before, where it gets the query key value and it performs that operation, that self-attention mechanism in these. But it can do it a little bit differently for each one of the heads because it has separate matrices that are multiplied by the query, the key, and the value. Okay. But it is doing that attention mechanism. The result, if you do have more than one head, they get concatenated back together. So you just have one output that comes from this multi-head layer. Okay, so don't get too hung up on the details. Just the overall, the main thing you should remember about the multi-head layer is it is implementing that neural attention mechanism in a way kind of like we described. Okay, so I'm going to wrap up this video and split this in 2. So in the next video, we will look at the transformer architecture, which uses a couple of these multi-head attention layers in the implementation of what's known as a transformer layer. So just to summarize what we've looked at so far, you should understand the basics, get an intuitive feel of how neural attention works. So it's at the heart of the generative AI kind of revolution. So it can be a powerful mechanism to build sequence models and generative AI models that don't feature recurrent layers. So we'll get an example of how we use these in the transformer, basic transformer layer to build sequence-to-sequence models. So basically, neural attention works by making features context-specific. Okay, so it computes a similarity or a distance score or an attention score, and it modifies the embedding to make the representation of a word more context-specific, according to the words that surround it in the sample. So a smart embedding space provides different vector representations for a word depending on the other words around it. And that's what neural attention mechanisms do. So in Keras, that results in what's called the multi-head attention layer. So this is a more generalized, so that key query value idea. So it can take 3 inputs, but you can use it for basic classification where all of the inputs are the same, or you can use it for sequence-to-sequence models where 2 of the inputs are the input sequence and 1 is going to be the target sequence. So that's it for this video. So stick with me for the next one. So we'll look at how we use those then in the so-called transformer architecture.